All right, so welcome back to System Software. Today we're starting our systems programming segment for the next couple of weeks. We'll look at some replicating some core tools, and we'll look at some of the common syscalls, system calls that you have available in the kernel. But before we get into that, let's quickly go over the homework. So the homework from last time was to read some introductory material about Linux programming from this book, the Linux Programming Interface. So the question was, how do you check what kind of error is thrown by a system call? So how do you check it? Yeah.
Check the error no level variable value.
Okay, you check the error no level value. Is that all you need to do? Yeah. First you have to see if there is an error. So how do you check if there is an error? Yeah, for many functions it's -1, and we'll go over today how you can read the documentation and it'll tell you exactly what the return values are going to be and what the error condition is. So exactly right. So you have to check and so in the kind of Unix philosophy, you have to check for these errors yourself. It's very easy to write systems code and just make these calls, not do any error checking because the kernel's not going to stop you unless you get a seg fault or something. And we'll go over that more today, this error checking. And it's kind of a good exercise in programming in general because it's very easy to program optimistically without thinking about what can go wrong. And in kernel systems programming, it makes error handling by the developer very, very explicit and very, very manual, very much do-it-yourself error handling approach. All right, any other questions on the homework? Yeah. Oh, Hello Project, right? Hello. Oh, yeah.
I'm fairly certain I'm getting everything correct, but unless I'm just missing something really obvious, if we can make clean times in a row, it's okay that we get directory does not exist error, right?
You mean file does not exist?
Or file, yeah.
It's okay. You can get around that by using rm-f instead. So rm-f will not. It won't. Yeah, it'll ignore those errors.
Okay.
So yeah, that's okay. That's okay. Yeah.
This is what I have so far. Apparently,
My vision is not that good to see that from here. So after class, I can take a look at it in office hours. So I have office hours today. So the project is due today, as listed. Hopefully it's clear. I know some people had issues with the PM AM difference between the homework and the project, but it is due today. You still have time till 1 minute before midnight tonight. Yeah, question.
when I try to do the win stuff, how do I do it?
Which one to submit?
The one where it's like the add, all that. It's like down. Right there, number 2.
Okay, so yeah, you can write git add and then the file name you want to stage for commit, and then git commit and the name of the file as well. So one way to do this, I don't even have the Hello project, but one way you could do this is to say git add hello.c. Let me, actually I don't have to go use this. Let me just make a hello directory. So you just do git add and the name of the file. Let me make the file. So you just say git add the name of the file. So when you type git status, it'll tell you have untracked files. That means those source files have not been documented in the repository database. Git add will stage it. So we kind of went over briefly last time what staging was about. You can collect together the individual files and lines that you want. Git separates staging and commit. And when you run git status, it'll tell you these are changes to be committed. That means they're staged. And then git commit and the same name of the file. It'll pop up your editor, put your message in, and now when you type git status, it'll tell you that there's nothing left to commit. If you see more stuff to commit, like untracked files, then you can add those and commit those. Does that answer your question? Yeah.
I use git add with all the files and then just use git commit.
You can do that. You can do that too. So I'm not going to go into too much detail about like software engineering practice in this class. It's best practice to pick the individual lines you want to commit. I pointed to, did anybody read that Google engineering guide? If you read that, that guide that I sent out, I have a link to it here. This actually goes into, so Google is very, very good at this collaborative engineering, the source version control, and they'll actually give you guidance on having good, I think these are, what are these, change logs, I think they're called. They're using this is the Google lingo. They'll actually tell you how to make these, basically how to make these commits in using Git lingo. But in this class, yeah, I'm not really checking that. Take processes, do senior design, actually work with other people who will, suffer from your, unclear engineering practices, and then you'll eventually learn how to do this in a good way. But here it's fine. Use Git however you like. Git is super flexible. You can add all the files if you want. There's a way to add everything that is untracked, I think, to there are like lazy ways to use Git. All right, other questions on the Hello project? Yeah.
So I ended up trying to revert it because I messed up somewhere.
Oh, you mean like running Git revert?
Yeah, like deleting it and stuff.
Oh, deleting the whole repository.
Yeah.
Had you already pushed to the?
I did, yeah.
So that database still exists on our grading server.
Okay, that's what, okay.
So yeah, deleting it locally just means your local copy of the database is deleted, and so you'll still, okay, so maybe you tried to push again and it said, I can't push anymore. So I think what to do in that case is to clone your repository again, and start from the database that you have. You might be able to do git push -f to force it, but I think that server does not, I think I tried that, the server does not permit you to do that. If you ran your own server, you could actually, like GitHub will, if you don't protect against it, you can actually force it to overwrite the branch, but I think Gitolite won't. So I think the best thing to do is just clone your existing repository, and just like you do in real engineering, instead of saying, oh, I messed up, let me go back and change history, just fix it going forward. So double check you use this self-check process to see whether you have all the files there, use git status to make sure all these are committed. Does that kind of help? There is actually a git revert command which will automatically undo a commit if you really think one of your commits is bad. But you can always just you could, for instance, make a commit that deletes all your files, and then you'd have the repository wouldn't be empty, but the current snapshot of it would be. So it's like an append-only log, a forward-moving log only. So if you have trouble modifying the current database, come to office hours and I'll help you work through it. But you should be able to just add more commits that will fix whatever issue you have. If that makes sense. Yeah. So the way to do that is to use this self-check section. This is exactly what our grader is going to run. Our grader is going to run this git clone command for your NID. And so if it works for you, it'll work for him. And so this is exactly, I told him, hey, look at the self-check, write your automated scripts to just run this for all the students. So that way, that's kind of the nice part about computing is you can check yourself. You don't have to rely on anyone to prove it for you. You can actually check for yourself whether it's correct. And the way to do it with version control is to just clone out a fresh copy of your repository so that you didn't accidentally miss some commits that you didn't push or miss some changes that you didn't commit. Other questions? Other questions on this? Yeah.
Could in theory the grader just make a make file without commands to run it everything?
Could you make a make file? What do you mean? A make file that doesn't have anything in it?
No. Could the grader, for example, make file to just run out those commands and then see if everything is working?
You mean a make file to run grading down? Yeah, absolutely. You could make a grading script to do that. You'd still need to have a list of the NIDs and input them somehow. I think I recommended he use Python to do this, but you could use make probably. Who submitted the project? Okay, pretty good, pretty good. So I do have office hours today, right after this, if you have questions. And remember that you can always resubmit as long as you make a submission today. So just to refresh you on the project rules, unlike in previous semesters, if you looked at my previous syllabi, in this version of the class, you have to make some submission first. Even if it completely fails, it doesn't work at all, make a submission. And then you can always resubmit again after that. But if you don't submit by today, then no resubmissions. And that's just to make sure everybody's like staying on track in the class. There were just too many people who waited till not only the end of the semester, but sometimes after the end of the semester to be like, I'm now starting this project. So I'm removing a little bit of that flexibility, yeah. Just pushing the Git repository, yeah. And that'll be the case for all projects. It'll just be submitting. So that's kind of the nice part for us about using version control, is that synchronizing your repository is the same thing as submitting your project. Just like you would do in like real world software engineering. You push it to some publicly available repository and now the whole world has it available to use. All right, everybody good on, yeah.
I have a question, more like an off-topic question about Git. If you were to share this with other people, your Git repository, do they have to also have like the same sort of system as you do? Like, for example, if you're using Bash, do they have to use Bash? Or do they use PowerShell?
No, as long as they have Git, the Git tool, then yeah, they can get your source code.
And Git is can be on any system. You have to install it, or
Yeah, it depends. Yeah, you have to install it on all systems. I know there's like somebody told me in Windows there's Git Bash, I think it's called. There's like a Bash tool or Git prompt maybe. I can't remember what it's called, but Windows has like a piece of software that will give you the Unix tools in one package, including Git.
like WSL?
What's that?
Is it WSL?
There is WSL, but there's one that's like native. I think it's called Git Bash. Windows.
Yeah, there's Git Bash, Git CNG, and Git GUI, which are all part of the Windows.
Okay, so there are Git tools for Windows. Git Bash, yeah, this is it. Yeah, so WSL is like virtualized, like you're running a different operating system. You're running Ubuntu, but this I think is a native tool. But yeah, Git is just it's a program, and as long as you can port it to other operating systems, then you can run that on other systems. You don't need Bash necessarily. All right, everybody good on the Hello project? So hopefully this kind of will work out a bunch of the kinks in the project submission process. That's why I did it this way. I tried to give a project where the programming part, as I think I promised you all, the programming part is really easy, but all the stuff around it may not be so easy, especially if you haven't seen this before. But this is kind of the classic systems programming, really just development workflow. Code in your editor, use build automation to build your project, and use Git to at least deploy the software, the source code for your project. So if you can kind of wrap your head around these three steps and at least a little muscle memory for some of the basic parts of each of these, editing, building, version control, then you'll be well set up for most software engineering workflows, because I think pretty much all of them in any professional setting will use these three stages, at least. All right, so hopefully everybody's comfortable with this, and then the next project I'll just ask you to make a makefile, and I'll still give you some Git commands because we're gonna create the Git repository in a different way. We're going to clone it from the beginning, so that way you won't. Anyway, you'll see it in the next project. We'll go over that. We'll go over that today. Okay, so let's get on to the main content of this lecture. First, a lecture of systems programming using files. Now, I think who's used like fopen, fseek? Did everyone learn this in like Intro to C? Is this covered in there? Okay, so. Did anyone ever just use open without the F, just open? Or read or write? All right, so these are the system call versions of those functions, so to speak. And we'll go into details about how fopen and all those other functions are actually implemented using the kernel. So which part of a software system manages files, at least in the Linux world? Or how are files created? Who does it? Who manages files? Where is the file system created? Does the disk itself have the file system on it? Sort of. Yeah. It's the operating system, and specifically the kernel of the operating system. The kernel is a library. We kind of talked when we talked about processes and files that the kernel provides this abstraction layer over the hardware. And so just to give you a little refresher, I showed you this picture in the very first day of class where we have all the hardware components down here that the electrical engineers spent decades developing, providing us an interface to their hardware to do things like run mathematical operations, store bits and bytes on physical media. And up here we have all the applications that we all love and use and want to use on computing. And in between we have the kernel, which provides this virtualized or idealized or emulation layer, whatever you want to call it, that kind of gives you this abstract or idealized form of the hardware. And why was this useful? Does anyone remember why bother doing this? Why not just why not just write your applications on the hardware? Why bother having a kernel at all? Yeah. Protects the hardware. So like if there are a lot of users and a lot of applications, you don't want one application to be able to blow away what all the other programs are doing. Yeah.
Makes it way easier to write applications.
It's easier. Yeah. Why is it easier?
You don't have to learn assembly code.
You don't have to learn assembly. And yeah.
It allows for better abstraction as far as concepts. You can use class, you can use things at higher level languages.
Yeah, you have abstraction. So related to what your colleague was saying, you can abstract away or find the commonalities in different hardware media. So the engineer who designed this spinning disk, they may have some bus, it used to be IDE bus years and years ago, and other pieces of hardware may use a SATA bus, and those have different sets of commands that you have to run in order to access your storage device. The kernel abstracts those away. Yeah.
So the kernel is the reason why your computer treats all the storage drives the same.
Exactly right. Yeah, that the kernel is what does that. The kernel is what unifies those. I mean, the hardware layer does it a little bit, like a common bus, but yeah, it's the kernel that makes it so. And if you remember when we talked about files, beyond just storage, files could be used for other things like setting up pipes or network operations. Doesn't necessarily have to be storage. Anything that has reading and writing can be modeled as a file in the Linux world. And so it's the kernel that manages those abstractions for you. And it certainly makes it much easier to write code, portable code, across different hardware. Yeah?
Where does the BIOS kind of fit? Does it make system software or is it more kernel?
So that's a good question. So the BIOS is kind of like a built-in kernel of sorts. Actually, nowadays with EFI, the modern, I guess you still call it a BIOS, is very fully featured. I mean, it's almost like its own kernel on its own. But old school BIOS was like a very, very low-level kernel, provided very, very basic operations like writing characters to the screen, almost like a very, very mini operating system. And that would be used by the operating system as a common way to start up. Because if everyone had their own way of initializing the hardware and their own set of commands to initialize hardware, maybe, it's like almost like a low layer kernel. And there are more sophisticated versions of this, like EFI these days. If you let me know, I can point you to, there's a good wiki page called, that I was showing another student. I think it's called osdev.wiki. This is a great resource if you want to learn more about the operating system development. And I think they'll probably go into biases in somewhere in here. Yeah, they'll go into detail about that. Okay, so for the system software is it's like applications in that it's sitting on top of the kernel and the hardware. What distinguishes it, it's kind of a vague term, but what distinguishes it is that it provides low-level functionality that bridges the kernel or the hardware and applications. And so when you're doing systems programming, you're working a lot with the low-level kernel abstractions. So for instance, the fopen and fprintf those are C library standard functions that call the kernel in order to help you manage files, reading and writing files. So let me go into the kernel design very briefly. If you read chapter 3 of the Linux programming interface, this talks about this. And we already talked about this already. It abstracts away hardware differences. And so one very simple way to look at the kernel is that it's kind of like a library. It provides this So it provides, there's this boundary between the kernel and what the kernel provides and what system software and other applications use in the kernel. So for instance, when you want to open a file, there's an open library call, just like any other library that you'd write. There's an open library call that you make from user space in order to ask the kernel, hey, I'd like to use the abstraction that you've created in order to read this data on disk. And so under the hood, this open command will do a bunch of low-level stuff in order to manage the layout of that file on disk. So here's the hardware layer. And the kernel kind of mediates file operations between user space and the disk, and also at the same time providing this common abstraction so that you don't have to worry about the hardware differences. And so this is sometimes called kernel mode or kernel space and user space. And in modern hardware, hardware from the last 40 years, this boundary is not just a library boundary, just like it is in C. It's enforced by the hardware. So that, and this is how protection works in modern computers. If you're running in a user space program and there's no holes in the kernel design or the hardware design, then you can't actually directly access any of the hardware. There are assembly commands that you can run to access hardware directly, but the hardware itself, the CPU, will prevent you from doing that. So if you write a program that has those commands, it will not run them. And if you want to access any kind of hardware, you have to go through the kernel, and there is a trick that is shown in the Linux Programming Interface book to go across this boundary. So if you're a user space application and you can't access hardware, then there's a special functionality in the hardware in order to switch to kernel mode so that the processor can start accessing hardware. So this is just the layer opened up a little bit. Each of these syscalls is defined in the kernel, and there's a special wrapper in a C library to make the transition between user mode and kernel mode. So as I kind of pointed out already, these system calls will operate on the kernel abstractions, processes, memory files. If you want to learn more about how the kernel creates these abstractions, take an operating system course or read the Operating Systems 3 Easy Pieces book that I've linked it in these notes, or you can Google it. So let's take a look briefly at this Linux programming interface diagram that they've got here. So it's not unlike when you write a C function and you want to call that C function. All that happens is basically a jump happens. So when you go to call that function, the program counter, you guys learn about this in computer organization, how functions work? You just have a branch instruction and it changes the program counter and goes to a different part of the code. Effectively the same thing happens with the kernel, except at the hardware level, we need to make this switch between user space, which doesn't allow us to do any hardware operations, and kernel space, which does allow us to do operations. And so there's a special interrupt. Who learned about interrupts in computer organization? They taught this, right? No? Did they teach this? A couple people remember. So interrupts are events that the hardware manages, and the operating system installs event handlers or interrupt handlers to run code once these interrupts happen. Like for instance, if network data comes in on the network, if the storage media writes to memory. And there are things called software interrupts that allow user space applications to send an event to the processor. And that event will transition to kernel space. And then the kernel will take over It'll run a little command, take over. And in the case of int hex 80, which is the Linux interrupt code that's used for transitioning to kernel space, the kernel will see that as a signal to run a system call. And in user space, you set up which system call you want, the arguments, call this interrupt. The hardware will enter the kernel for you, and the kernel has the definition of this, the actual code for this system call. It executes it. Once it's done, puts the return value and any error code back into user space, and then your program continues on, just like any other function call would. So this is super brief. This is more like operating system level stuff. But any like quick questions on this this design? Yeah.
So are these calls being ran mostly, or is it just kind of like, I think it's like
A different what?
are these like system calls being run inside the kernel?
They're run inside the system. So that, well, the terminal is a program running on the operating system.
Okay.
Is running on the machine. And so, yeah, this is all running on the same machine. This is all running on the same machine. So it's this is running on one machine. If you have one processor, it's all running on the same processor. And this whole design is really around hardware protection to prohibit the user space applications from directly touching hardware. And this is the scheme that, I don't know who set it up. Intel kind of popularized it. They have these rings of protection. And they just set up this mechanism where in assembly you can trigger the processor to enter this different state, enter this hardware, kernel mode state. And because when the system booted up, the kernel took control of what programs would run or what code would run whenever these interrupts happen, prevents user space applications from accessing protected hardware. Yeah.
So that, for a command there, just controls the permissions to access the file.
So it's not permissions for the file. This is permissions to run a set of hardware instructions. So you can think of like your ISA, your set of instructions that the CPU supports. In protected mode, there's only a subset that you're allowed to run. And when you switch to kernel mode or protected mode, I think it's called supervisor mode. I can't remember the term. Then the set of commands you're allowed to run is larger. Does that make sense? So there's only a subset of commands you're allowed to run in user space. And when you trigger this interrupt, the kernel has already installed at boot time code that will run the kernel code. So in memory, you basically have like a set of code, that's the kernel code, that you can only enter through these system calls. And that's the only code, barring any vulnerabilities, that's the only code that can run in supervisor mode, that can run with the full set of hardware processor instructions that the processor has. Does that kind of make more sense? All right, so take an OS class. This stuff is pretty cool. You can actually even write your own kind of simple versions of this. If you can actually boot your machine without having to have an operating system. You can write your own programs that run just kind of on the bare metal. And I think this page will go through that. It'll actually go through some examples of just booting to your own program, and then you'll have, you won't be in protected mode. You'll be able to run whatever hardware instructions you'd like. Okay, so let's go over system calls. From our point of view, as the programmers, they work just like C functions. You call them just like a C function. They give you a return value like a C function. And here, there's a wrapper, as they call it, a wrapper in the C library that handles all of the argument passing and collecting the return value and error codes, handles all that for you, so the function will behave just like a C function. There's one little difference, and that's in error handling. Error handling is done in this standard way in the Unicode, and we'll go over those details of how to use that. If you want to see what system calls are available, oops. You can use the man page to show you a list of the system calls. And so here's the list of them that Linux provides. You can see there's a lot, probably many that you don't use. Let's see if there's any that are in common use. Probably in Intro to C, probably you use C library functions like fopen. So if I search for fopen here, there's no fopen, but there is open, the open command. It's different from fopen. Yeah, it's different from fopen. And let me go into what these differences are. All right, so when you run man, you'll notice that there's this number here 2. That's not an argument to the function, and this is not a function. And so the man pages are divided into these predefined sections, like sections of a book or chapters of a book or volumes. And we can see what those are by kind of self-referentially looking at the man page for the man command, man. And so these are the sections of documentation we have. So section 2 documents the system calls, and section 3 documents the library calls, for instance, fopen. And so open is the system call that allows you to open, read, write, close. These operate on files at the kernel level. And when you use fopen or fprintf or fscanf, these are C library functions. So those don't directly call the kernel. Instead, they use the kernel file operations in order to implement more convenient file handling for you. So that's why libraries are a type of system software, because they mediate your application and the kernel. And so when you're trying to look up the documentation, you can explicitly put the number of the section that you want to look up the function in. So if I try to look up open, which is a system call inside the C library documentation, it's going to tell me there's no entry. But if I use fopen in section 3, voila, I get the documentation for fopen. If you ever forget, there's a -a, which will open all of them, all the ones that match. So in section 1, which is for commands, it'll open that. When you quit, you can go to the next one. You can go to every section that has a match with open, if you forget, and it'll always tell you which section you're in here at the top. Okay, so that'll be useful when you're writing your systems code, because it's hard to remember exactly the details of these library calls. I mean, that's also true for C standard library calls. This will tell you the function signatures, and more importantly, it'll tell you return value, so you know exactly what to expect, and it'll tell you error conditions, what the return value is for an error. And when there's an error, it'll tell you all the different kinds of errors that it'll throw, what the error state will be when you have an error. Okay, so let's look at the system call versions of these functions. So as I guess everyone learned in Intro to C, you have fopen, fprintf, fscanf, and I guess fclose, right? Fclose as well. What's that? fc. Oh, fseek, right, to move within a file. And so the system call versions of these are open and write and read and close. And I guess seek is not, I think seek is some functionality that's provided by the library for you. Actually, there is seek. Reposition, okay, no, it is provided by the kernel as well to reposition the location. Okay, so that's how you can look up the documentation for these calls. All right, so the Unix way of doing error handling is to give it to the developer, give it to the programmer. The operating system is going to give you very little help in error handling. And if you want to look at some of the background behind this, there's this kind of classic essay called Rise of Worse is Better about this Unix design versus other kernel designs. But in the Unix world, this kind of error handling can is kicked down the road to you, the developer. So basically, whenever you're doing any system calls, or really any library calls, you should have kind of reflexively think, what are the error states of this? What will happen when this goes wrong? And actually, in any programming, you should be thinking, worst case, what's going to happen if this goes wrong? Or how do I even represent something going wrong? So here's the Unix way of representing something going wrong. This is the open command. So you give it some path. There are flags for saying whether you want read only or write only, etc. And to handle the error, we check the return value to see if it's the return value associated with an error. And then this error number, error NO, is set for you to some error code that corresponds to the error that you got. So that's the basic process. You run a syscall, look at its return value. Every time you run a system call, you check its return value. So if you looked in a Linux programming interface book, you'll see lots and lots of error checking after every call. There's always an if statement checking. Sometimes the function is, one little trick in C is that you can put the function call in the if conditional, which you can't really do in many other languages. But every time you run a syscall, you got to run a check for the return value. And so a lot of these system calls have -1 as a return value, but not always. Oh, why can't I search that? Oh, it's the wrong open. So now I'll give examples of all the system calls that you'll need for the projects in this class. But if you ever are in doubt or you don't want to look through my code, you can always do the man page and look and see what the error return value is. So in this case, it says on error, -1 return, and error number is set. Questions on this? Pretty straightforward, right? Just takes a little discipline every time you run a system call to do the error checking. And in this class, so one of the benefits of this from the system programming world of doing error checking is that you can more gracefully handle this error. Like, let's say you're writing a program that, maybe it's like a drawing application that has somebody's, doing drawing. You probably don't just want to quit the application if you encounter any syscall error. You might want to save that person's work or try to recover from the error or repeat the open. There's all sorts of different designs of your system that you can implement when error checking is left up to you, the developer. Now, yeah?
Why are you using just normal opens and you're using the F for them? Why are they both the F sources?
This is because I want to print stuff out more easily. And I want to use the easier library for printing stuff out. So the differences for read and write and printf and et cetera is that this has like string processing. This format string can be you can put like placeholders in it. The system call version, which is just write, is just working with raw bytes to a file.
I meant why can't you just use normal?
I just want to. Sorry. Why use? Sorry. Why I'm using fprintf instead of printf? Because I want to write the standard error.
Okay.
That's why. Yeah.
So if it outputs a -1, it's not an error?
If it outputs a -1, it is an error. So this is saying if open returns -1, then according to the documentation, -1 is only returned on an error, or on an error, -1 is returned. You would hope that it's if and only if. And so this piece of code is your error handling code.
So
Yeah.
I read on the thing that error node is a global variable that's written to by a wrapper function.
Yeah.
And so that means that you don't ever define error node anyway.
You never have to define error number. Yeah.
You automatically,
Whenever an error happens, this is a pretty. What's that?
is it given to you by the library?
The error number.
Error node, standard library?
You include this. You can include this for the definition, but it's kind of like I can't remember if it's done by. I think it is done by the C library. I don't know if it's done by the C library or by the kernel. I don't know the step where the error number is being set, but yeah, it's like a hard coded name that the C library, or probably not the kernel, but the C library will just set this value for you after if there's an error. Yeah.
I just want to confirm, the SPV
This is so if you remember the standard I/O, the stuff on standard I/O, every process is opened with or run with 3 open files: standard in, standard out, and standard error. And when you're running the bash terminal, standard error and standard out go to the same place. They go to your terminal window. But it's just a convention for separating the kind of real output of your application. So for instance, we're going to do a file listing application. All of the content that is supposed to, when you list files, that should be the output. Whenever there's an error, you don't want to pollute your output with that error, so you keep them separate. So for instance, if I'm doing ls of some file that doesn't exist, this text is being printed out to standard error, whereas if I just say ls hello.c, this is standard out. You can't see this on the terminal, but you can kind of prove it to yourself by redirecting standard error. This is how you redirect standard error to not print. Whereas if the file exists and I redirected my standard error, I can still see standard out. So this is just a convention in the Unix world. Use this convention for your applications because I kind of rigorously define or try to extensively define your output, and the output standard out does not include the error messages. All right, other questions on the basics of error handling in the systems world? So basically every time you use a system call, do this check. I mean, for this class, all you really need to do is quit. We're not going to be checking.
Could you add p error to that so you get an actual?
That's a really good question. So somebody knows about p error. Who's used p error? Did you guys learn this? Okay, not many. All right, so there is a helper function called p error, which will interpret error number for you. So if you look at this man page for say open, I keep doing the wrong one. In this error section, it'll list out all the different ways that the kernel will report that your system call went wrong. And each one of these codes here corresponds to a number. I think they're defined with macros, probably. So there's a unique number for error number that can be referenced with this name. So these are all the ways that your kernel can, for the open command, can go wrong, can say, I can't do this command. So for instance, if it's the exist error number, it means that the path already existed. And so this is very common in computing systems and in programming, that the handling of errors is just as detailed and comprehensive as the handling of expected output, which for every programmer you should be aware of, error handling in your code. And so that's very, very detailed. It's standardized, I think, for all of these system calls. Each system call has its own set of errors, and this whole set of errors across all system calls is all predefined by the kernel. So for instance, there's no more memory available in the kernel, which would be pretty bad if that happened. Not a directory. So this is the extensive list, permissions issues. This is the extensive list of all the things that can go wrong when you call the error. And now for this class, you're not going to have to do any detailed error handling. But if you're a systems developer, you can use this to implement various error handling methods for a robust system. So just like I was talking about, you have a drawing application. Let's say you have an airplane that's flying. You don't want to stop the computer. You want to try to recover from the error. You want to either rerun it again or signal to the user that something went wrong. Like for instance, hey, you don't have permissions to access this file. What do you want to do now? For a lot of the low level like ls, you just run the command again. But if you're running a long running system, you may want to employ better error handling options than just like crashing or stopping. Okay, so p error will just print out print out a message. It'll translate that error number into an error message for you. And I'll show an example of this in a little bit when we do some actual systems calls. All right, other questions on error handling, because this is going to be pretty critical. It'll also, so as you'll see, as I'll show, if you don't do the error handling, the kernel will not necessarily stop for you. The program will continue running, and you maybe get very, very unexpected results may be very hard to find what's causing this. Like, for instance, you may have a little typo in your path, and the kernel couldn't open. And then when you keep trying to read or write that file, you're going to get errors somewhere else in the program where the error actually didn't happen. So make sure every time you do a system call, do error handling as well. And you only have to exit. There's also this convenient exit code for you, exit failure, that you can use. Oh, that was your question. So so these are, this is kind of the principle of no magic numbers in coding. So you want to have names instead of numbers. And so the system in header files defines a bunch of names for these magic numbers. Like each of these error numbers possibilities has its own name in a macro. You've got exit success and exit failure for conventions on what exit code to use for your application. And so this is the basic pattern that you'll use. Check what the return value is for an error for your system call that you're running, but this is the basic pattern of error handling that's all we're really expecting in this class for error handling. Yeah.
How do we know what to pass to the error?
Oh, this is just your error message. So this is like printf. It'll just print out open, and then it'll print out the error message. Let me show an example of that in a second. But there, I don't have any. I don't think I said we're going to actually check the value of that. We're just going to check to make sure that you exited properly, or that your program doesn't have any bugs because you didn't do error handling. So, for instance, we'll give you a file that doesn't exist, and then this is how you gracefully handle that. You actually checked the error. Open will throw an error if you give it a file that doesn't exist, and then, or at least for read, it'll give you an error. And so we'll just throw you files that don't exist and see what your program does. All right, other questions on error handling? This is probably the most salient thing to remember from this. All system programming is really about error handling. Yeah.
Do you have any recommendations for configuring vim or Emacs stuff before runtime, or you just?
Oh, that's a good question. You mean checking whether you've checked the error code? You could. I don't know if there are analyzers that will do that, but it would not be hard to write a static analyzer to do that. You can take my compilers class and you can write that as a project, or you can do it as a bonus project. But it's not that hard actually to write a very, very simple checker. It won't necessarily catch all cases, but you could write a checker that will automatically do this. But this is very beyond this class. This is a program analysis task. But you certainly could. I don't know if there's any Emacs plugins. Google it, see if that exists. I feel like there must be. It's a common thing. So check yourself. And so the rule is, if you're using a system call, check the error condition. And the only error handling you really need to do in this class, perhaps with one exception in the shell that we'll talk about, is just exit. Okay. So I put a full example of using error number here, but I'm gonna skip ahead just for the sake of time, so we get into all of the other system calls that you'll need for the LS project. Okay, so let's start with files. So the only ones you need for this project are opening files, reading files, and closing them. And for the reading tonight, for the homework. Actually, okay, I didn't provide this as a reading because I actually thought people had used open, and read and close already, but it was fopen that people used. So if you want to read more about these, use, this is the chapter to read in the Linux programming interface book.
Didn't you assign us that the other day?
Did I assign you 4? No, it was only 1 and 3. So if you want to learn more about these, read this. But I'm going to go over an example here that should be all you need for doing the LS project. So maybe before we go on, let me go over what the LS project is briefly. Then I'll go into all the system calls you need. Yeah.
I'm having the same problem.
Yes, ma'am.
I keep
Okay.
getting to use
That's
this.
Is there maybe there's an issue with Eustace?
So, how do I forward on here?
Do you mean to get into Eustace right now? Oh yeah.
What if you're out
Oh, me?
No, I got.
It's there. But, okay, so I don't know. I don't know. We'll have to email the IT. So if there's an issue and the people no one could submit, yeah, let me know. It sounds like several people are having issues. So if you can't submit, so just let me know. Go on EdStem, and then other people, pile on and say, yeah, I can't go, and then I'll have a strong signal that something's wrong with Eustace. Yeah, not sure what's going on. Wait, no, it's asking me for. So when you put in your password, it just denies you? Try now, maybe?
Even though I was in, I tried to do it again, and
Deny me. All right, something's going on with Eustace, unfortunately. But yeah, just let me know on EdStem. Keep me up to date, and we'll see. We still have, 11 hours for submission. But yeah, let me know. I can. Yeah, of course, if Eustace isn't up and you can't submit, then you won't get penalized for that. All right, so let me go over the next project, my ls. So remember the ls command. What does the ls command do? List all the files in your directory, or a directory given on the path. So everyone is going to write their own version of ls called my ls. It's much simpler. It's only going to take a single argument. That argument is optional, just like with ls. It can be relative or absolute. And if you don't provide the directory, it'll be the current working directory. What's the current working directory? That's how you can find it. You can find the current working directory. So every process is started up with a working directory. So in your command line shell, when you're in bash, that directory you're in that you can type ls, that's your working directory. And of course, error handling. And so the output, let me just give you an example of the output. So it's going to be very different from the ls command. It's going to be a list of every file, including dot and dot, which if you list out the directory, it's going to be in every single file, and some metadata and data about these files. So I'll go over this in detail, but basically you'll read the number of links, the kind of file it is, its size or number of files in the directory. And if it's a regular file, then you'll print out a little preview of the file. Yeah.
So are we like writing this as like just a normal C file? Or are we like
Mm-hmm.
something else?
This is going to be a C program, and you'll use these system calls to do it. So please don't, use other system calls like fopen and stuff like that, which will make it easier. Use these system calls, and only these. For printing and stuff like that, of course, you can use the standard libraries. But for doing file management, use these system calls. So we already went over PR and exit, and so now let's go over these three sets. So we'll go over how to open and read files. We'll go over how to get metadata about files with the stat command, and we'll go over how to read and navigate directories, which you'll need in order to list out all the stuff in the directories. All right, questions on this? Yeah.
There's a bunch of header files.
Yes. So in my example code, you'll see all the header files will be there for the example that you need for it annotated. All right. So let me actually just go into the code. So this is going to be. Oops. Okay, so this program here is a
It's a files.c.
well, the source code is the final source code will be in the class notes, and so I will that will be available on the website. But I would just want to walk you through step by step this code. So let me build it up. It's on the website. It's on the website. Okay, so sorry. In each of these examples, it tells you all the header files you need. And so let's just start with some sorry, I'm just setting up my okay, so let me get rid of all of this. So this is the kind of just template for showing you examples. This isn't necessarily what your final program will look like. Although you can use code similar to this to read in a path. Remember, it's optional. This is a not optional path. Does anyone have any questions about this code here? Oh yeah. Any questions on this?
Where did type out all the source code, or do we just like?
Oops, I wasn't used to this. Yeah. Boy, you can cut and paste as well.
I don't know how to do any of that stuff.
Cutting and pasting?
No, I know how to write all that source code.
Well, you can use the code that I provide as a template. If I provide it on my for you for class, that it's not cheating to use that code if it's in my notes. Okay, so anybody have questions on this? This is just reading in one argument from the command line and assigning it to this path variable. I think everyone's done this, right? Who's read in arguments from the command line in Intro to C? Only half the people. Okay. So this is the code to do it, to read in an argument.
By an argument, you mean like
Just an argument on the command line. So when I run files, this is my argument here. So let me so just to show you what this looks like here, I'm just recompiling files, and if I print out path, it should just print out. Oops, it's commented out. So you can see all this program does is it takes the one command line argument and prints it out. So I can change this to. So what should be printed out when I run this program?
this is my argument.
Whatever I typed in. So this is my argument. So whatever I put here on the command line, that's going to be what gets printed out.
Wait, how do you do all that?
Do all what?
Like this is my argument, and then the command line argument.
So this is just bash.
Oh, just a bash script.
This is the terminal. This is the terminal. So this is how you run C programs. I think everyone's done this, right? You compile a C program and you run it with // Okay, so I now have some, whatever the command line argument it is in the path variable, to use the open system call. Here I'm going to open it up as read-only, which you won't need to write files for this project. And so I've just done a system call, open. What's the next thing I need to do? Error checking. So if you are in any doubt about this function or this system call, you can check its return values, and it tells me, okay, -1 means that I had an error, so I need to write a condition. So what can I use to, or what in this class at least is the error handling strategy in this class? Print it out. So p-error you can use to help you print it out. You can put whatever message you really you want in there. That's going to read error number for you, and then just exit. That's all you need to do for these broken in these broken cases. Okay, so if I run, here's my program. I open a file, and if I get an error, I print out, I run the pre-error command to print out the error. Otherwise, I pass that and I call printf no error. So for this execution here of the files program, what's going to be printed out by my program?
Error.
Open error, unless this file exists in my directory, which you've kind of assumed that it didn't. So this is what p-error does for you. It takes whatever message you put here, and then it gives you this nice message that corresponds to error number. So in contrast, if I had put a file that does exist, like the file source code, this does not get triggered because the return value is not -1.
Could you put in whatever you want where you wrote open?
Yeah.
Or just defines?
It just gets printed out. Oops, I don't have the error there. Okay, so now that we have a file open, and so at the kernel level, each file is just assigned a number. Called open file is assigned a number called a file descriptor. That's why it's an integer. And so with that file descriptor in hand, I can read from this file now that it's open. So this is a little bit of kind of common style C coding. I hope everyone has who's done like arrays and buffers and reading. I think everyone should have this in Intro to C. If you don't, let me know. Come to office hours. I can help go over some of this. But this is kind of pretty standard C. I'm making a character buffer, just an array of buff size. How many elements are in this?
What is INST?
Oh, that's a typo. Thanks. That's a typo. And okay, and so here is my read system call. Read takes in a file descriptor. It takes in a buffer. So it takes in a file descriptor, takes in a buffer, and it takes how many bytes you'd like to read. So this is kind of different from like scanf or other helper library functions. Here you have to be really, really precise about exactly what you want to read. You have to handle the buffer yourself. So this is what the kernel provides you directly, and probably why you learned fopen and fseek and because that avoids having to manage a lot of this very precise management of file contents. So how much should I read in? Well, we don't want to overread our buffer or overwrite our buffer, so we'll read in that much content. Okay, I've done a read command here. So what do we need to do next? Error checking, very good. We need to do error checking. So let me put it to do there to do error checking. But before I do that, let's run this. And okay, so if I run this and I didn't have this error handling, first of all, let me show you what happens if I don't have any error handling at all and I just run open. So this is, I've commented all this out and I just run open. What do you think is going to happen? Nothing happens. A silent failure. So the kernel reported the error to you, but the kernel's like, okay, the developers got it. He handled it, but we didn't. And so if I had failed to do this error handling, and then I went on and tried to read the file with this file descriptor, now what do you think is going to happen? So let's look at the, okay, I don't think this tells you what a file descriptor, oh yeah, so we have some error handling on the read function, like FD is not a valid file descriptor. So as you correctly said, we're going to get some kind of error, but where is this error going to happen? So let's run this. So we've got open with no checking, and then we've got read with no checking. What's going to happen? It says no error. So the kernel didn't care that you didn't handle the errors. It's just going to go on, and then when you go to try to do the project and you miss some bug, you're not going to get the right output. because you had a silent error. It's going to look like you got the right error or right output, but yeah.
So it accesses some portion of the memory that you pointed to, right?
So this one doesn't. So so let's do some error handling on read to see what the kernel said about this read command. So I gave. So all right. So how do we? Let me not do this code cloning. Let's do this by hand. All right. So let's look at the return value for read. So on error, -1 is returned. So -1 equals, where's the return value of read? It's in bytes, good. And I am going to do a little code clone here because I am lazy. So let's just say we had an error on read. All right, so what value is read getting for FD here in this execution of the program? It's getting -1. Yeah, whatever open was. And in this case here, where I have a file that doesn't exist, it's -1. So here, I've got an error that I caught on the read command, but where's the error? The error is not on the read command, right? The error was actually here on fopen. But without doing that error checking, your program is just going to proceed as if nothing was wrong with values that you don't think that you don't want for the rest of your program. And so that's kind of that's the critical thing here. So even if I had done no error checking at all, nothing happens with my program. It has a 0 exit code because it's us, the developers, that define what errors are in our program. Linux kernel did its job. It gave us the error messages. We just decided to ignore it and pretend that everything was okay to our user. Yeah.
So the error no value is just the last one? It won't be like a list of all the errors?
No, it'll be whatever the last one. If you want to save all the errors, yeah, you can do that. But yes, it's only set when the error happens. So if you try to read it again later, or you could even, I don't know if it's constant, you might be able to write it. You could probably get your program to write it. But it's only set when the error happens. So it's not, if this error didn't happen, error number is not going to be set. It's going to be some stale value from a previous error. All right, so here is open and read with proper error handling in both cases. So the error on the open is caught, but if I have a real file here, no error. Read had no error, open had no error. All right, questions on this? So this is just opening and reading a file, all these lines of code, to do it correctly and safely in the Linux world. All right, so let's print out. So another difference between fopen and read is that the system call works with bytes. It gives you the raw bytes of the file. It doesn't assume that it's a text file or anything like this, like scanf and other features. It just gives you bytes. So if we want to write out these, we could just iterate over our little buffer here. Now we can assume they're characters, which might not be a safe assumption. They're all files. But this is the printf for. Has anyone seen the printf for characters? Does anyone have to do this? I'm not sure what people have seen or not, so you can ask me questions if you haven't seen stuff. But here, what's that? Okay. So that's a good question. So let's look at %fs. Yeah. What do you think is going to happen? Oh, yeah. What's your question?
Well, I was going to say that %3 is actually correct, but if you're doing a character array, that's %3 is correct.
Yeah, %3 will interpret it as a character. %s will interpret it as a string. So what's the definition of a string in C? Null terminated. Yeah, very good. Null terminated. There's nothing here that guarantees null termination. We just read the first 10 bytes, if available, of our file. If there's no null string there, then yeah. What? I?
Yeah.
Oh, yeah. Thank you. Yes, it should be buff size. Thank you. But here, let's print out the string and see what mayhem it wreaks. So you can see here we got the kind of classic problem that you see if you don't have a null terminated string. So it looks like there was a null terminator at some point. But yeah, this is not a string in the C sense. This is just literally bytes. Strings are an interpretation of bytes that require that they're null terminated. Characters are interpretation of bytes that require that they're ASCII code, basically. Okay, so let's see what happens when we print out each character of this buffer. Let me just print it out without new line. So here we get the first 10 bytes of this file. And indeed, if I look at the beginning of this file, then yeah, these are the first 10 bytes of the file. This includes stuff here. Questions on this? And then close, same deal. I'm going to do the little trick here where we run close inside of the if condition. And same thing with close, although close kind of matters less because Linux kernel manual recommends you don't try to reclose or anything. So there's not much you can do if close fails.
So if you basically have it read through the whole file, you kind of have like a rudimentary cat.
Yeah, exactly right. Exactly right. Yeah, this is like the beginnings of doing cat. Now, dealing with read is kind of annoying because you have to read them in predefined chunks. You have to say how much to read every time. And so C standard libraries will do buffering for you and like make it easier to do that. Yeah. How can close fail? Let's see.
When it's done, there's nothing to close.
Nothing to close. Yeah, the file descriptor is invalid. If you try to call close again, it got interrupted. So this is a big annoyance of dealing with Linux system calls. Technically, you may have to retry system calls, actually. So these are all the error conditions. So you can just read the manual and see what the error conditions for close are. Yeah?
What's the difference between using exit failure and exit, and you just place the 1 in the notes?
So one is a magic number. Exit failure is like a POSIX standard for whatever that code is. I actually don't know what exit failure is, but we can see what it is. So it is 1. It is 1, I guess. Yeah. So you don't have to remember the number. You just use the code. All right. Let me go over one more set of system calls. Let me go over directory reading because this one is critical for your project. All right, so we're going to start the same way. And there are only a couple of commands you need. Just like with files, you have open directory, read directory, and close directory. And so these are actually not system calls, these are library calls, but the manual recommends that you don't do the actual system calls for these. But they're still pretty low level. So let me just show you quickly how these how this works. There's a data structure, or actually there's a type called directory. When you open a directory under a given path, it gives you a pointer to this directory listing. And so after we call a system call or even a library call, what do we need to do? Error handling. So look at the manual. In this case, if the pointer is null, it signals an error, and we can use the same error handling approach that we have for pretty much everything in this class. And the way you can look at what all the contents of your directory are is to use this readDir function. readDir takes the pointer that you got from opening the directory, and every time you call it, it gives you the next entry in the directory. Very, very low level. You don't just have a nice array where you can look at everything. You just have to execute this instruction over and over and over. And so the kind of C tricky way to do this is to run read directory in a loop and print out whatever information you want about this directory. So this is all in the reading for tonight. I've given you the reading for this for tonight. It's all in the manual. Oh, it is forking. Oh, sorry. Okay, reading is here if you want to look at it. So I'll go over this more next time since it looks like I'm running out of time to go in more detail. But But you can also look at my examples online for doing this, and also look in the manual. So here's what happens when I run this program here, opens the directory, and then iterates over each entry in the directory. I get a listing of all the files in my directory, including dot and dot dot.
Where you put it inside of a while loop.
Yeah, exactly right. Yeah, you just iteratively read each element of the directory. Yeah. Does order matter? No, order doesn't matter. It'll be in directory entry order, which you can see with ls-f. All right, so I guess you guys decided class is over. So class is over. We'll finish up the last command next time, which is just file status. That's pretty straightforward. And all right, everyone, have a good day. Give me 1 sec. Let me turn off.